if you want. Hey, everybody. My name is Kun, and Chris and I are here to present the trusted execution environment protection for firmware integrity. Well, a little bit about ourselves, and I'm a principal software engineer working at Microsoft's core UFI team, and I'm mostly have been working on the x86 supervisor, and most recently there's some FFA supports inside the UEFI forum. So Chris, on the other hand, is a main evangelizer for the FFA supports in the Windows ecosystem, and he's also an expert for the Windows boot. So today's agenda will start about some key takeaways about the keynotes for this presentation, and then a little bit of introduction for the evolution over the past few years, and then we're going to do some deep dive into the x86 and ARM side of the privileged execution isolations. And then we're going to end up with the OS integration. So the key takeaways. So what we're hoping is that after this presentation, you will try to understand the firmware requirements from the Windows side, so that the firmware we shipped can be secure core PC compliant. And then next up would be we can learn some about the history and the story for the industrial collaboration on this privileged execution environment isolation. And then most importantly, which is the third point, is that try to apply some of the techniques that we talked about here into your firmware. And if you would like to take one step further, come and collaborate with us, and we can make the whole industry a bit better. So the acknowledgements before we jump into the true details and the information, I want to mention that this is efforts and the collaboration over the past few years from multiple silicon vendors and manufacturers, architectural designers, just to name a few, Intel, AMD, Qualcomm, ARM, and more. So yeah, we would not be here without them. So to begin with, what is the trusted execution environment? So this is an abstracted terminology to describe the privileged execution environment. So for x86, this is specifically talking about the management mode, where, well, during boot, we set up some of the SMI handlers and then issue the MMI, and the system will just transition into a separate execution environment. Similarly, for ARM, this is invoked by the secure interrupts, and we can thunk system into trust zones, and platform get to use this for their proprietary stuff, or some are just a standard. For example, the UFI variable operations, or hide some secrets in there, whatever. So this provides the flexibility, but I think in general the mileage may vary, because people get to do things without the awareness of the OS. That's great, but sometimes it poses a very high risk. Just to name a few here, just because the fact that it has free access for almost everything that OS owns post-boot, it is actually very critical for this code to be right, and it's actually very hard to write bug-free code. So here are some CVEs that we listed here. The SMI handlers are the main vulnerability that we talk about, and whenever bug occurs or being exposed to the other folks, we tend to find out that issuing the bug fix is actually pretty hard. We start with validating the patch actually fixed the issue, and then try to make sure that there's no regression, and then try to issue the updates if the device is still being supported or maintained. A lot of time that's not the case. And even publishing the updates, well, we may need to go through the capsule updates, but how do we do that? So a lot of hurdles on the way, which is why we're trying to deploy this isolation mechanism in place, so that we can prevent it from early phase during development even. And the isolation here specifically means to have a core component so that we restrict the user component to have access to the necessary resources only. And we can configure this boot environment during boot time, and then the runtime is pretty much locked down, and whatever this configuration or policy we're sticking to can get reported to the OS, so that the OS get to authenticate or audit the policy the trusted execution environment is sticking to, and then yeah, OS can give a thumb up or thumb down. So just to know that this is critical for the DRTM security story that Windows uses for the secure core PC verification. Now, we can dive a little bit deeper into the x86 and see how that is being done, or how that is being done, at least for Microsoft. Again, a little bit more history on this side. I think we just heard about the PPAM, very great. Truly, the Intel started this initiative for trying to impose the isolation for their SMM mode with the PPAM, which, as we just heard about, this is some monitoring module that gets to audit the page table and get it reported to the OS. The OS get to know, oh, whether my hypervisor is being exposed to the SMM or not, etc. And then later on, Intel take it one step further by deploying the hardware shield. Somebody call it Devil's Gate Rock, or DGR for short, which is a monitor or supervisor for the SMM environment. So it will restrict the access to some more critical resources, such as the MSRs, I/O, save states, etc. In the meantime, AMD also contributed to this evolution by developing this SMM supervisor, and they also engaged their coprocessor, PSP or ASP these days, to validate the SMM environment. And back in around 2021 is when Microsoft coming with our firmware attack surface reduction efforts, which is a more software-oriented effort to do almost the same thing by ensuring the trustworthiness for the execution environment, the privileged execution environment. So this is the first time where we embraced the standalone MM. And we also migrated the SMM supervisor from AMD to support the standalone MM. And there's also this C component that we're going to talk about, which is the supervisor of the supervisor. So, okay. So first thing first, standalone MM. I think we have evangelized this idea for many, many times here and there. But this is a PI spec-defined architecture to manage the management mode. That is supposed to be common across different architectures, including x86 and ARM. So a few key advantages here would be that it eliminates the Dixie dependencies, or even PEI dependencies mostly, so that it does not call out to the protocols or PPIs resides outside of the standalone MM environment. And then it also supports the earlier launching, for example, SEC or PEI. We can already set up the standalone MM foundation, and then from that point on, supposedly, there's only going to be the MMI communicating between the secure world and non-secure world, right? And if a module is clean enough, we will have relatively easy adoption, which means that one INF and one entry point file, we pretty much can convert it from the traditional MM to the standalone MM. So we have reused most of the SMM code with very minimal change. People can take a look at the EDK2 history on how the standalone MM is being supported. That's pretty much it. So all that I'm trying to say is that this poses a very clean cut for the potential for the hardware isolation, meaning that with some hardware configurations, we pretty much can use the hardware to perform that dashed line over there, and just start to enforce the isolation between the non-secure world and the secure world, or SMM and non-SMM. And that sounds great, but how do we configure the hardware in this case? That's where the MM supervisor start to kick in. As I mentioned earlier, this is adopted from the AMD's SMM supervisor. So it is also a privileged separation-based component where it's a core component so that it runs at ring 0 and demotes the user code into ring 3. So this starts to give us some natural boundary between the user and the supervisor mode code, which means that the MSRs, the IOs that needs access needs to go through our syscall gates, and syscall gates is being verified by a build time baked-in policy. Similarly, we're imposing a very strict page table on top of the user code, meaning that the non-SMM pages needs to be specifically unblocked, even including the core component itself. So all that information, the MSR, IO, save states, and the page table will eventually getting coalesced and reported to the OS so that OS get to inspect the state of the security of the MM environment, and we are going to give it a score, whether thumb up or thumb down, we'll see. Well, sticking to the spirit of this conference, this is a open source project through Project Mu. So I put some link towards the end of this slides so people can take a look at it, if you will. But over the past few years, we have received a few reports on the security analysis. So yeah, thanks for the participation. And it has already been deployed across multiple Microsoft platforms. So the few new CVMs that I listed here, they're not applicable to our platform. So I think it is proven worthy. But what if this supervisor went rogue? Right? How do we make sure that this actually makes sense? So that's where the supervisor of the supervisor that I just mentioned start to kick in. We call it SMM Enhanced Attestation Mode, which is the C. This is a solution we developed specifically on Intel silicons. This is a STM-based solution. STM meaning the SMI transfer monitor, which is very similar to PPAM. So this is also being invoked as a part of the DRTM routine so that it will be measured by the Intel TXT technology. So what it does is that it's acting like the inspector of the supervisor. As part of the DRTM routine, it will come in and try to check on the healthiness of the supervisor. And if it checks out, the inspector will instead report the policy over to the OS instead of the supervisor reporting the policy itself. And yeah, which means that it actually runs as a higher authority. Again, like I said, it's policy-based, so and also open source. I also posted the link towards the end of this slide, so people can check out. And I think our plan so far is that we're going to try to support a binary release so that other folks can get to use it as well. Okay, how does it work? We can dive into a bit nerdy details. So can you actually see it? It's fine. Okay, starting from the build time, we actually built the supervisor that I mentioned earlier. It also all boils down to some EFI file, so that's fine. And alongside of the build environment, so we're also creating some metadata, which includes the expected value and the default value outside of the build. So we bake that metadata into the C core, and then we carry that as part of our EFW. So during boot time, the supervisor is going to get expanded, loaded into the SMM RAM, and start to execute. So over time, well, so will the C core. C core will be placed at the beginning of MSEC. That's a separate technical detail, so we can read the spec about. Oh, okay. Over time, the execution is going to change the supervisor image, meaning the code may get self-patched, or the global variables will get updated. So that's where those stars and dots come from. And we need to actually verify that this start to make sense. So that's where, upon booting, the OS will start to invoke the DRTM, and the TXT is going to measure the MSAC content and then hand off to the C core component that we just talked about. So the C core is going to use the metadata it baked in to take a copy of the executed SMM supervisor core into the MSAC area and use that metadata to try to see, whether the content right now matches the expected content, and use the default content to override the current copied image. So after this process, we actually reverted most of the executed image back to its original state, other than some paddings and then some non-zeroed data sections that we do not care. And then we can undo the padding and the relocation so that the image will get put back to its original states, mostly. And then we can calculate the hash on it and then compare it against the original hash during build time that we carried in the metadata. If that's a match, great. It means that the executed SMM supervisor is trusted. So we can also trust the policy that we are going to extract out of it. So yeah, that's our current story for the x86. And I'm going to hand off to Chris to talk about the ARM side.
Thank you. Yeah, so the ARM ecosystem is a little different and a little bit the same at the same time. It's the same in that we have a bunch of different silicon vendors that all kind of implement their own mechanism for having isolation in this. So you can think about, we have Ampere and Qualcomm and our own Cobalt 100, and everyone is going to manage their secure world a little bit differently. Now, the problem is that this doesn't necessarily scale so well, because when we're talking about the x86 ecosystem, where we have a pretty limited number of silicon vendors, the ARM ecosystem has the potential to grow significantly, and it's not really feasible for us to have a bespoke implementation for every single silicon vendor on how we maintain and how we expect isolation to occur. And to clarify things a little bit and to ground us for those who aren't familiar, ARM is very similar in terms of x86 in terms of having a different execution mode that has the same more or less hierarchy as the normal execution, in that you have EL0 and EL1 and EL2, where you can have different components running with different levels of privilege and isolation from each other. But for example, so for standalone MM, as Quinn mentioned earlier, we have typically that running in secure EL0. The problem is that by architecture, anything running in the secure world has full access to the non-secure physical address space most of the time. And so standalone MM has the ability to read and write the OS hypervisor. For no particular reason, it doesn't need that access, but that presents a significant amount of a risk, because if there's a vulnerability there, then what that vulnerability can then do is significantly increased. And so really the point they're making this slide is that we can't really rely on bespoke implementations. We really need standardization. And this is where our friends at ARM have been very, very useful and helpful, because they have defined the Firmware Framework for ARM, or FFA A-class, which basically is a specification that standardizes the roles, the entities, the components, the expectations of various different entities that play a role in managing or communicating between the non-secure world and the secure world. And this provides a number of benefits. One is that because we create standard pathways through the secure world, we're reducing customization in things like EL3, which is the most privileged execution mode on the AP. So we really don't want things there that we don't have to be there. But it also creates well-contained boxes for all the different vendors that take part in building a platform and making their roles well-defined and their components in the CPU well-defined. You have the OS running in its regular mode. You have the OS hypervisor or a third-party hypervisor running with its roles and responsibilities. The silicon vendor would provide the EL3 firmware and the secure partition manager, which I'll talk about in a second. And then the OEMs or IAVs have the ability to add their extensibility and their value add within the secure partitions. And they're all contained from each other, and they all have well-defined roles and boundaries. The secure partition manager is something I want to call out in particular, because that is the highlight of this conversation around trust execution isolation. There is an open source implementation of the secure partition manager named Hafnium that I want to call out as a good point of reference here. But that's what I want to talk a little bit more about. So the Secure Partition Manager, or Hafnium for the open source implementation, is something we really expect to be part of the silicon vendor's like secure boot story for the SOC firmware. So that is, it should be directly validated during boot up by EL3 or BL31 or whatever the implementation is. It should be directly validated and known to be owned by the silicon vendor. So we don't necessarily need the same independent validation mechanisms that we have for something like C, because it is a more static root of trust in that way for the silicon vendor component. Now the SPM can take many different forms. We mostly expect it to be implemented as a hypervisor, which means that all of the isolation is really enforced through regular hypervisor mechanisms, right? So you have the stage 2 translation for the MMU, which provides the easy ability to say that, you know, standalone MM is running at EL0. It must go through translation schemes that it does not control to access memory. And so it has no ability to access the hypervisor or the TPM or anything that it doesn't really need access to. Everything it needs access either needs to be granted to it or it needs to be in its original system manifests. And then all this being controlled by the Secure Partition Manager, we can then query these things and change these things through standardized SMCs. And when I say query it, I mean, so the OS, something we've been working with ARM on is adding some standardized calls for actually pulling out information about what secure partitions have access to. So there's a new standardized call in 1.3 alpha something of the FFA spec. It is available now, that defines a new non-secure resource info get, which allows us to query the Secure Partition Manager. The Secure Partition Manager will then go and parse the stage 2 translations as well as secondary data for translations that might be possible for the secure partitions, compile that and return a list so that way the OS can see all the different memory regions that belong to it, as far as it's aware, that have asynchronous access from other AP firmware. So with that, let's talk a little bit about the interaction with the OS, because it's something we've alluded to in both mine and the x86 side from Quinn. So the isolation by itself does provide great benefit. Like, you have significantly reduced attack surface, because if one of these binaries become vulnerable, the number of things you can then do with that vulnerability is significantly reduced. It becomes a lot harder to jump from one vulnerability to then introducing another vulnerability. Just because you've compromised standalone MM doesn't mean now you can monitor what the user is doing on the system, at least not directly. And so it makes it significantly harder for attackers to jump around between components if they find a vulnerability in a single one. So that's great. But this does play a role in a greater security story, especially in DRTM, as mentioned earlier. And for those who aren't familiar, DRTM is a runtime security mechanism that allows you to use like CPU functionality to effectively reset the CPU state to a known good place, do a measurement of a new binary, and launch it. So that way that binary is executing against a measurement in a way that is more or less isolated from the execution of things that came before it. And the isolation is the key part, right? Because the T environment is an extension of UFI in a lot of ways and a lot of other components. And so, well, how it knows if it's isolated is really secondhand information coming from something like UFI. And so it's very important that there's integration between this isolation mechanism and DRTM to ensure that the OS has the ability to properly evaluate its isolation during the DRTM process from things running in trusted execution. And the way that typically takes form is that during the DRTM mechanism, we would expect that trusted execution, asynchronous execution at least, gets disabled. And the OS has some period of time in which it can query for policies, check its isolation, make determinations based on that before it proceeds and re-enables that asynchronous execution, being SMIs or secure world interrupts. And if it decides it doesn't like that policy for whatever reason, we can do a number of things. We could reset the system. We could extend new measurements in the TPM, do whatever we want to either lock out or control the flow of the system from that point. So to drive that home a little bit better on the x86 side, or this is specifically Intel, AMD has its own mechanism, but I mean, we have so much time. And this is what's being used for C. So you will go through DRTM. DRTM will disable SMIs, this being Intel TXT in this case. The STM will get measured into one of the DRTM PCRs. Then DRTM will launch the OS provided or bootloader provided DLME, which will be the post DRTM measured binary. That can then go and query the STM, query C, to get the policy. The process that was described earlier of validating SMM will happen then. Policy will be returned. OS evaluates this for proper isolation, make sure that things that we're using for hypervisor memory are not the communicate buffer, for example. And then at that point, we can then re-enable SMIs. And the point here I want to drive is that at this point, the expectation is the OS and SMM are running in more or less mutual exclusion from each other. They have, because traditionally we were expecting the SMM to have full access to the OS, and we don't have any access to SMM, but that causes problems. So now we are trying to create a paradigm where we have more or less mutual exclusion. And so the ARM mechanism, this is a little forward-looking. We're still working on some of these things, but this is the same, we should have the same concept of we will go through DRTM. DRTM will suspend asynchronous execution in the secure world. The DLME will be launched. Again, we'll query the SPM or hafnium for the policy, and then we will do the same evaluation we do on x86, and then we will tell the DRTM mechanism, hey, we are ready for secure interrupts to be re-enabled. So in conclusion, we kind of want to drive a 3 following points on what this is about. I mean, first is that T isolation is a critical thing to achieve for sustainable security, because realistically, there's a number of components running in these environments. As mentioned, they're not necessarily easy or frequently updated, and having isolation increases our resilience to vulnerabilities that will almost definitely occur. And as part of this, this is just part of ways this could be done. There's many different things that people could do to implement isolation. These are the ones that we expect right now. But definitely there should be OS involvement, so that way we can achieve those security stories mentioned. We would hope that OEMs and IFVs are thrilled to have this isolation, because it reduces the risk of your own code and reduces our risk and reduces everyone's risk if we're just isolated from each other. But ultimately, this really represents what we believe needs to be an evolution in the security model we're used to. We've become very accepting of the fact that there are components that have effectively God mode access on the system, and that's fine because we trust ourselves and we never write bugs and we're not going to have any issues with it. But realistically, there are going to be issues. And so we need to be investing more in an idea of mutual distrust between different components running on the AP, in our case, between firmware and the OS. So that way, when we are less vulnerable to overall impacts on the system as individual components, which, I mean, is overall better for the platform, overall better for the user. And then lastly, I want to drive home that there are several open source implementations for these technologies that we would really like people to, or encourage people to use, to consume, to contribute back to. In particular, the C effort in the supervisor that we publish open source, and then ARM's hafnium implementation, which is also open source. And we would really encourage IHVs to adopt these, to consume them, provide feedback, and contribute, so that way, overall we can have a greater security story together. And with that, we'll open for questions.
Great talk again. I have a question. You're talking about both for ARM and x86. You talk about C for x86 side of things, supervisor of the supervisor, and EL3 for the ARM. And you mentioned these are open source. Are these binary? How is the OS doing the attestation to trust these are proper? Like, is it coming from IHV as a signed binary, or is it a part of SOC solution or something? How do you integrate that part of it? So,
I mean, it's a little bit different for the different implementations. So for C specifically, how it's done is that there is basically we have like a signed manifest of the hash. And so that way we know that the C implementation is authored by Microsoft. We have something similar for Intel for their PPAM, where basically we get the measurement that comes from DRTM is in the TCG log. We can verify that that it was measured by that and that it is the STM measurement. And then we can then compare that to our signed hash that we have and make sure it is basically through indirect means signed through a known authority.
Can I confirm? So you're saying the C, even though part is open source, but it is signed by Microsoft?
Yeah. So, I mean, well, ultimately, whoever is providing, because of the verification mechanism for the STM, we have to know what hashes of the STM we trust and don't, because OEMs can load whatever STM they want, right? And so right now, the two hashes we'll trust for STMs are PPAM and C. And that's one of the reasons we want to do the binary release, so that way we can make this available to other OEMs. But yeah, I mean, we need to have something to root it in, because there's no static root of trust on this.
And when you were saying EL3, firmware coming from this, that was signed by Microsoft?
No. So for the EO3 is a little different because the STM doesn't have any CI story necessarily for when it's loaded and launched, which is why we need this kind of indirect measurement and then validation of the measurement. On something like the Secure Partition Manager or EL3, those should be rooted by CI or the platform secure boot for the SOC. So we expect that to be rooted back to the trust of the.
So, yeah, just to confirm, so in that case, you don't have OS a way to check if it's coming from it's implicit that's trust.
Yeah. I mean, there are measurements in the PCRs, and there's measurements that happen in PCR 0, and then additional measurements that happen during DRTM, but we're not directly expecting those to be from a specific authority per se. Okay. Though we do use like auth blobs and other things to verify they're the measurements we expect, et cetera.
Thank you.
I have like so many questions, so I'll try and limit myself. This feels very much like when the secure world was introduced in the first place, where we go, oh, we can't trust the thing, so let's add something small that we can all look at, make sure it's all bug-free, and then we can trust it, right? And now we go, oh, no, it's too big, and we can't trust it anymore. Let's do isolation. Now let's do something else that's really small. We can look at it, it'll dispatch this thing, and so on, right? So I feel like we're just pushing it all the way back to the root of trust in some way, which I guess this is just the way that it works. There's only so many ways to skin a Wookiee. But my real question is, how does this relate to, and I think my ARM colleagues might be talking about this later, we have a new thing coming in architecture called RME, where we add another bit on a bus. Now we have 4 worlds, so secure world doesn't have to actually see everything in the system. We can isolate it. We move the EL3 root monitor into its own super privileged mode. You are not supposed to put anywhere in that root monitor like we've been doing so far. It's supposed to be just the world context switch. And then instead of the normal world operating system wanting to be secure, we move it into this 4th world where we can attest it using platform security, TPMs, and that kind of stuff. I know that FFA is involved in that as well. And it seems like it's going to be solving quite a few of the problems that you currently have that you're trying to solve by isolating the secure and non-secure world.
Yeah, I mean, so I know I'll caveat that we are still familiarizing ourselves with like the new address spaces in ARM v9 and Realms. Though, if I recall correctly, there's like a exclusive non-secure access and then like a shared access now that secure world and non-secure world both have access to their physical address spaces. I can't remember the exact nuance. But yeah, I mean, so things moving into like Realms, things moving into these more isolated environments don't necessarily matter for this. But for things like, if you think communicate or trying to access variables, these are things where we require some amount of data sharing between the non-secure world and the secure world today. So my assumption is that no matter what, we're still going to continue to use some amount of shared memory. And so whenever there is that access scheme that allows non-secure and secure access, we're still going to require this restriction. Like I correct me if I'm wrong in terms of the different modes, but I'm pretty sure that still exists even in the new, more boxes implementation.
Yes, I think the solution here is the use case where rather than expecting the non-secure to be able to make sure to get this evaluation, instead you move all of that compute into the realm and then do crypto attestation of that. And then you don't care about the non-secure world being snooped into because there's nothing running there anymore.
No, I agree. Realms has got a lot of potential for having more secure execution. And then one comment back on like the adding more boxes that you mentioned at the beginning. One of the things that we do like about this in particular is it does add more boxes, but now the point of the boxes are a little bit different. Like we have like better containment of, the silicon vendor code versus IFV and OEM code versus the OS code. And so, yes, we're creating more layers, but the hope is that these layers are better defined in what their purpose is, rather than just being more layers for less code up top. because realistically, the secure partition manager and EL3 basically have the same level of access and authority on non-realm machines. But yeah.
I have two questions for you. You mentioned that this is showing up in Mu. Does that mean that you're bringing this to market independent from secured core PC? And then relatedly, how do you guarantee that a platform is in fact secure, that filters or IMMU programming has happened in a way to protect secure world from kind of DMA-based attacks?
Okay, there's twofold. Could you please could you please repeat the first one?
So you mentioned this is showing up in Mu.
Yeah.
Does that mean you're trying to bring this to market independently from secured core PC?
Well, this is a EDK2 compliant component, so you can get to pick and choose that. I admit that the implementation is different from what other folks have been seeing, which is the standard standalone MM core plus the PISMM CPU standalone version. So that's, yeah, this version is going to be different, but it's still compliant to the EDK2 boot flow. So if you pick and choose that, so then you are going to have this benefits that we just talked about. And for the IOMMU and the DMA attack, I think even the standalone MM core that we have in EDK2 currently mitigates that by copying the entire content into SMM before reading it. So that's one part of it. So where, by the way, another benefit is that actually lock down the SMM RAM immediately after the MM foundation is set. So that's at least the DMA into the SMM RAM is not going to be down. And then if we copy the content from the COM buffer into the SMM RAM, we pretty much just mitigate that part of attacks. Sure, there's going to be the aspect that people like to nest pointers inside that we have not found a legit solution yet, but yeah, just try not to use that scheme if possible at all.
Thank you.
Yeah.
All right, one more question.
So I have a question about the C. I'm not really familiar with it. So is this a C and MM supervisor specific to Intel solution for STMM support?
Yes, that's correct.
So for AMD x86, if we want to have a STMM support, we really don't need this solution, right? Is that correct? We're going to using AMD's SM supervisor. Is that enough, or we still need the C to do this?
AMD have a different story for the DRTM, so it's going to be different from C.
But we don't need these two components.
That's correct, but
Correct?
that's correct for now.
But okay, there's something going on. Okay, so for the C and the MM supervisor, these components resides in the Windows. It sounds like to me like that, not on the Flash. Is that correct?
You also carry that as part of your Flash, yes.
Oh, so part on the Flash and part in the Windows.
The authentication parts, which
C is on the Windows.
no, C is also in the Flash.
Also in Flash.
Yeah,
So
they're both in Flash.
If we picking the computer using the Linux, is that solution going to work?
The OS authenticating the policy parts probably will not be there.
Okay. So
It could. There's nothing that's stopping it, but I don't know if they have that implemented in.
Okay, yeah.
so that means if Intel's x86 are using STMM, we're going to have some challenge because their solution may not working with STMM.
To clarify, so the SMM implementation would still work as expected.
But the secure PC, that's this
Yeah. So, all the implementation of this is available. So if Linux wanted to implement talking to C and verifying C and getting the policy back, I don't think there's anything necessarily stopping it. We might have to, discuss that to make sure. But All of these things are in the open and available if they want to use this validation. And if not, they can still use DRTM as they do today.
So Microsoft going to supporting if Linux want to do it, right?
I mean, it's all open. I don't see why not.
To do the signing, is it Microsoft?
For this, yeah, because so for the STM, this like we have to have some way of knowing the known hash. If they wanted to just carry known hashes that they trust because they know the expected binary drops, that's also possible. I don't know if I can talk about whether or not we could, the public portion of the key, provide that or something like that. But yeah, I mean, they'd have access to all the same information. The only detail there being maybe the public key for validation.
So if we want to talking more about the detail, who is the contact in Microsoft that we should talking to? For the secret part, whatever.
Yeah, I mean, yeah. Yeah, I will direct you to my boss.
Okay, we got it. We know the name. Thank you.
All right. Thank you. Thank you very much.
All right.